Then in our last video, we were looking at instantaneous velocity, which is the slope of the tangent line drawn to the curve at any point, and then instantaneous speed would be the absolute value of that. Now, if we want instantaneous acceleration, that would be done the same way. You would take the slope of a tangent line drawn to a velocity time graph, and we'll look at that later in this video. But there's an equation method of doing it. So if an object has a motion described by the equation x sub t equals y, or 4 plus 3t plus 8t squared, determine its velocity at 2 seconds and its acceleration at 2 seconds. What we do then is take the first derivative of our curve. So we'll have dx dt, and just using the power rule, that'll end up being 3 plus 16t. Now if I want to know my instantaneous velocity then at 2 seconds, I'll just plug in 2 for t. So I'll go 3 plus parentheses 16 times 2. And that's going to equal then 35 meters per second, assuming that we're in meters. It doesn't really say in the question, but that's okay. Okay, now what about finding the acceleration at 2 seconds? Well, then we'll take the second derivative, okay, of x with respect to t. So that's again the power rule here. So that's going to then just be 16. So assuming that we're in meters, that'll be 16 meters per second squared. So what this tells us, we have a constant acceleration then that's involved with this motion here. So if we were to think about what the graph of this equation would be, then the velocity would then be just a straight line going upwards. And acceleration then would be a flat line going over here somewhere. And this, of course, would be at 16. So velocity is just increasing the entire time. But I noticed, though, that we have a negative velocity initially. So initially, we would then be below the x-axis. I'm not showing that here for simplicity. Okay, so let's go on to acceleration. So if I want to have the average acceleration equation, again, average acceleration would then be equal to the integral of t1 to t2 of a sub t dt divided by t2 minus t1. And what that equals the integral then of dv, just like we had dx from before, of t2 minus t1. So then that's then going to be equal to v, the definite integral t1 to t2, if I take the integral of dv. So what does that end up being? Well, average acceleration then is v sub t2 minus v sub t1 divided by t2 minus t1. And that equals our all-familiar equation from AP Physics 1. Acceleration is the change in velocity, okay, over the change in time. So you see that we're following the same process from calculus that we used to derive our equation then for average velocity, except now we're doing it for average acceleration. Of course, there are graphical interpretations of that. If I want to get my average acceleration, okay, I will then pick 2 points on my graph. So if we call this one here T1 and this one here T2, okay, it would then be the slope of the line that connects these 2 points together. So average velocity then would be equal to the change in velocity over the change in time, just like we did in AP Physics 1. Now what about the instantaneous acceleration? Well, that would be equal to the slope of the tangent line, okay, drawn to our curve at any time value that we wanted. So if I want acceleration instant, that's going to equal the limit of delta v over delta t as delta t approaches 0. So you can see very similar to what we've done already. But now we're dealing with the change in velocity over the change in time. Okay, in our final video, we're going to be looking at how the Fab 5 are derived and some examples of graphing cues.